While the Internet is a datagram network, many alternative network architectures, including those of ATM and frame relay, are virtual circuit networks, and therefore use connections at the network layer. These network layer connections are called virtual circuits. Let's now consider how a virtual circuit service can be implemented in a computer network. A virtual circuit consists of 1. A path, the series of links and routers between the source and the destination. 2. The virtual circuit number, one number for each link along the path. And 3. Entries in the forwarding tables in each router along the path. 3 components: a path, a virtual circuit number, and entries in the forwarding table in each router along the path. A packet belonging to a virtual circuit will carry a virtual circuit number in its header. Because a virtual circuit may have a different virtual circuit number on each link, each intervening router must replace the virtual circuit number of each passing packet with a new virtual circuit number. The new virtual circuit number is obtained from the forwarding table. How does the router determine the replacement virtual circuit number for a packet traversing the router? Whenever a new virtual circuit is established across a router, an entry is added to the forwarding table. Similarly, whenever a virtual circuit terminates, the appropriate entries in each table along its path are removed. Why doesn't a packet just keep the same virtual circuit number on each of the links along its path? Well, for one thing, there may be more than one virtual circuit active, and a router might be serving more than one of them. And if that were the case, it's also possible that a virtual circuit number might already be in use somewhere else. Remember, the forwarding tables are being updated continuously as changes occur on the network, in which case a router will have been informed by its neighbors what virtual circuit number it is using for each virtual circuit. In a virtual circuit network, the network's routers must maintain connection state information for the ongoing connections. Specifically, each time a new connection is established across a router, a new connection entry must be added to the router's forwarding table, and each time a connection is released, an entry must be removed from the table. Note that there is no virtual circuit number translation. It is still necessary to maintain connection state information that associates virtual circuit numbers with output interface numbers. The issue of whether or not a router maintains connection state information for each ongoing connection is a crucial one. There are 3 identifiable phases in a virtual circuit. First, there's the virtual circuit setup. During the setup phase, the sending transport layer contacts the network layer, specifies the receiver's address, and waits for the network to set up the virtual circuit. The network layer determines the path between the sender and receiver, that is, the series of links and routers through which all the packets of the virtual circuits will travel. You recall that is one of the primary functions of the network layer, determining the route. The network layer also determines the virtual circuit number for each link along the path. Finally, the network layer adds an entry in the forwarding table of each router along the path. During virtual circuit setup, the network layer may also reserve resources such as bandwidth along with the path of the virtual circuit. So the network layer determines the virtual circuit number of each link, adds the forwarding table entry in each router along the path, and then reserves resources as necessary. The second phase is data transfer. Once the virtual circuit has been established, packets can begin to flow along the virtual circuit. Third is a virtual circuit teardown. This is initiated when the sender or the receiver informs the network layer to terminate the virtual circuit. The network layer will then typically inform the end system on the other side of the network of the call termination and updates the forwarding tables in each of the packet routers on the path to indicate that the virtual circuit no longer exists. There is a difference between virtual circuit setup at the network layer and connection setup at the transport layer. Connection setup at the transport layer involves only two end systems. During the transport layer connection setup, the two end systems alone determine the parameters like initial sequence number and flow control window size of their transport layer connection. Although the two end systems are fully aware of the transport layer connection, the routers along the path within the network know nothing about it. On the other hand, with the virtual circuit network layer, routers along the path between the two end systems are involved in the virtual circuit setup, and each router is fully aware of all the virtual circuits passing through it. Take a look at this. Initiates the call, accepts the call and responds. The call is connected. The circuit is set up and data begins to flow. The messages that the end system send to the network to initiate or terminate a virtual circuit and the messages passed between the routers to set up the virtual circuit are known as signaling messages. And the protocols used to exchange these messages are often referred to as signaling protocols. In a datagram network, like you see here, each time an end system wants to send a packet, it stamps the packet with the address of the destination end system and then pops that packet into the network. As shown in this figure 4.5, there is no virtual circuit setup and routers do not maintain any virtual state information because there are no virtual circuits. Now we're talking about a datagram network here. As a packet is transmitted from source to destination, it passes through a series of routers. Each of these routers uses the packet's destination address to forward the packet. Each router has a forwarding table that maps destination addresses to link interfaces. When a packet arrives at the router uses the packet's destination address in the header to look up the appropriate output link interface in the forwarding table. The router then forwards the packet to that output link. Let's look at another example. Since an IP address is 32 bits in length, it would be impossible for the forwarding table to have more than one entry for every possible destination address. There would be more than 4 billion possible addresses. Suppose that the router has 4 links, numbered 0 through 3, and the packets are to be forwarded to the link interfaces as shown here. With this style of forwarding table, the router matches a prefix of the packet's destination address with the entries in the table. If there's a match, the router forwards the packet to a link associated with the match. For example, suppose that the packet's destination address is one that you see here, 11001000, 00010111, 00010110, 10100001. Because the 21-bit prefix of this address matches the first entry in the table, the router forwards the link to interface 0. If the prefix doesn't match any of the 3 entries, then the router forwards the packet to interface 3. Although this sounds simple enough, there's an important subtlety here. You may have noticed that it is possible for a destination address to match them more than one entry. For example, the first 24 bits of the address match the second entry in the table, and the first 21 bits of the address match the third entry in the table. When there are multiple matches, the router uses the longest prefix matching rule. That is, it finds the longest matching entry in the table and forwards the packet to the link interface associated with that longest prefix match. Although routers and datagram networks maintain no connection state information, they do maintain forwarding state information in their forwarding tables. However, the timescale at which the forwarding state information changes is fairly slow. In fact, in a datagram network, the forwarding tables are modified by the routing algorithms, which typically update a forwarding table every 1 to 5 minutes or so. In a virtual circuit network, a forwarding table in a router is modified whenever a new connection is set up through the router, or whenever an existing connection through the router is torn down. That could easily happen in a microsecond time scale in the backbone of a Tier 1 router. Because forwarding tables in datagram networks can be modified at any time, a series of packets sent from one end system to another may follow different paths through the network and may arrive out of order. To the contrary, in a virtual circuit network, the packets from a message all follow the same path. Well, that concludes the section comparing the two basic network architectures of the datagram networks and the virtual circuit networks. And this is a great time to take a break. So let's stop right here. You take some time to look over your notes, maybe go back and review the video and update your study guide. And when you're ready, come on back to lesson 4, where we'll begin our study how addressing and forwarding are done in the internet.